Hello everybody. In this video we're going to be looking at exponential functions. Exponential functions are non-algebraic, also called transcendental functions. Alright, here's a basic equation of an exponential function. F of x equals a to the x. Well, what's a? Well, actually a is going to be a number that's greater than 0 as long as a does not equal 1, as long as x is a real number. Alright, so this is a little bit different than the polynomial functions that we've been studying, or the rational functions, in that now we have a number base and a variable exponent as opposed to a variable x base and a number exponent. So we're going to record some examples over here of exponential functions. Notice the exponent is a variable, but the base is a or a real number, and 1/3 is a number that's greater than 0 and it's not equal to 1. Another example of an exponential function. And yet a third example of an exponential function. Parentheses aren't critical. I just wanted you to see that sometimes I use them, sometimes not. It doesn't have any effect on the problem whether you use them or not. Notice that 1/3 and 1/8 are both numbers that are less than 1 but still greater than 0, and 7 as a base is still greater than 0 too, but not equal to 1. Part of our work with exponential functions is going to involve evaluating exponential functions at a given x value. So for these examples right here, we're simply going to plug in pi everywhere we see x, and go to our calculator and compute the value. Before we do that, let's go ahead and make a recording of what we're going to do on the calculator. So everywhere I see x, I'm going to replace it with pi. So this function evaluated at pi would equal 2 raised to the negative pi power. So you're going to go to your calculator, you're going to type in 2 raised to the negative pi, and we're going to record the decimal answer to 5 places. Alright, for this next example, we're going to evaluate this exponential function with a base of 3/5 or 6/10 as the decimal. We're going to use the x value of 3/2 to figure out what that answer is. Go to your calculator, type in 0.6 raised to the 3/2 power, and record 5 decimals. Okay, look at these two examples right here. For this function we have 50 times e raised to the 4x. You might be thinking e is a variable. However, it's not. Let me take you back and remind you about pi. Pi is an irrational number. It never repeats, nor does it end. And we know pi, have come to know pi, as approximately 3.14. E behaves the same way as pi. It's an irrational number, not a variable, and it's approximated by 2.718. So, not quite 3. All right, let's evaluate this function at 2 100ths. Keep the 50, keep the e, raise it to the 4 times 0.02 power. All right, go to your calculator, type in 50 e. E is found under, I guess it's down far left column, it's on the LN button. It's actually 2 buttons above the on key. I encourage you to go ahead and type this in and make sure and confirm that you get what I get here to 5 decimals. Alright, let's evaluate this function at positive 1/3. Everywhere you see x, replace it with 1/3. Well, this is as easy as typing in e raised to the negative 1 power. This is the result rounded to 5 decimal places. So on your homework, when you're asked to evaluate an exponential function at a given x, go ahead and make this recording showing what you're going to be doing in the calculator. All right, the next thing that we're going to do is we're going to graph some exponential functions. So we need to see, kind of dig in and look at the basic behavior of an exponential function, and then after we graph some parent functions of exponential functions, we'll be able to graph some other functions based on transformations of these parent functions. All right, so in this next set of problems, we're going to create a table of values. That's why these tables are given. Then we're going to sketch the graph and identify any asymptotes that these graphs might have. All right, so for 2 raised to the x powered, these are the x values, the input values that we want to put in for x in the equation. This becomes 2 to the negative 2. Well, that's going to be as easy as typing it into the calculator. However, I want to remind you that with a negative exponent, we're going to move the base of 2 to the denominator of a fraction and change the sign from negative 2 as an exponent to positive 2. We know that as 1 over 2 squared, or 1/4, but when we go to plot it, we're probably going to want to change that to a decimal. Next one, 2 raised to the negative 1 power. That would be the fraction made with the positive exponent of 1 over 2 to the first. Let's go ahead and change that to 0.5. That'll help us when we graph it. If we weren't graphing, if that wasn't the objective, I'd probably just leave my answer as 1/2. All right, so back up to 2 to the x. Now let's let x be 0. Anything to the 0 power is going to be 1. Now let's plug in 1. 2 to the first power is just simply 2. Scroll down a little bit here. 2 squared is going to be 4. All right, so let's go back up. You've got those points in front of you there. I might have to kind of take them off the screen a little bit, but I'm going to come back up here to the grid. All right, we're going to have to go ahead and scale the grid. It looks like our input values go from negative 2 to positive 2, so maybe that's negative 1 and that's negative 2. Likewise, 1 and 2 over here. All right, so it's our responsibility to scale the y-axis. We'll take a peek at your y values down here. My y values go from 1/4 up to 4, so that gives us an indication of how to scale the y-axis. So I want to go up as high as 4. So maybe each of these tick marks would be 1. All right, let's return to plotting. I'm going to plot the point negative 2, 1/4. So negative 2, 1/4. Well, here's 1, a height of 1, so 1/4 is probably about right here. Next ordered pair would be negative 1 and a half. So go over to negative 1, go up to a half. So these y values are increasing. The next order pair would be 0, 1, because if my exponent is 0, anything to the 0 power is 1. That's my y-intercept. Notice that your y values are increasing. Plot 1, 2, and 2, 4. And let's make a prediction about what the graph would do if it continued to the right. Well, if it continued to the right, it looks like it's going to get more steep, the graph that is. The y values are going to get greater. Let's make a prediction over here. What would happen if I traveled to negative infinity? Well, that would mean I'd have values in my table like negative 3, negative 4, smaller than negative 2, and those outputs would be actually less than 1/4, which means they're going to get really, really close to the negative x-axis. So I'm going to try and draw this graph so that it's not touching the negative x-axis, because it won't, and then coming up here and picking up these points. And I know that as I travel to the right, my graph's going to get really steep. So make sure and put arrows on the end of your graphs, extend them to the left and to the right. We have an increasing function. As we look at it from left and right, our function is increasing. Okay, do we have an asymptote? Yes, we do. Actually, the x-axis serves as a horizontal asymptote, and the equation of the x-axis is y equals 0. Something else I want to point out here is notice that this point 0, 1 is obviously at a height of 1. Anyway, the vertical distance that I would travel, okay, so that my graph has a horizontal asymptote, this vertical distance where this graph is contained just is a distance of 1. And that becomes important when we go to sketch a graph. All right, so let's look at the next example. I think it's going to be, let's see, so I don't have to scroll up, it's e to the x. All right, so everywhere you see x in the original problem, let's put in these x values. So I'm going to come back over here and put 2 to the x and y equals e to the x. E to the negative 2. That's weird. I don't know why it's jumping. Let me scroll up a little bit. It's still jumping. Maybe because I'm in a table. This is equivalent to 1 over e squared. You'd go to your calculator and compute that value. It's really small. For the purposes of graphing, I mean, I don't need 5 decimals. It's just 0.135. I don't even need that much. E to the negative 1 is equivalent to 1 over e. Go to your calculator, compute that value. 0.368. So notice the progression of these y values as x increases, as my x values increase from negative 2 to negative 1. My y's are increasing also. So my function should be rising. E to the 0, anything to the 0 power is 1. E to the first, well, that's 2.718. E squared, compute that value on your calculator, and you're going to get 7.39. All right, just notice the progression of these y's. They're getting larger as my x move from left to right. So my graph should be another graph of an increasing function. But these y values compared to the previous y values are greater. So my graph should be a little more steep. It rises more quickly. All right, if we want to scale the y-axis, notice my greatest value is 7, so I might want to try and go up to, I guess, 8. Actually, let me use the same scaling as the last one, because I do want to make a point here. So if this is 1, 2, 3, 4, similar, a little different, 5, 6, 7. You don't have to label every single tick mark, just enough to get the general idea of what the increments are. So negative 2, in my table, I have to plot 0.135. Well, 0.135 is a lot smaller than a quarter in the previous example, so I have to even be closer to the negative x-axis. Well, I'm going to be kind of limited in how I can draw that. But what's happening is that these values over here are hugging the negative x-axis a little more closely than they are over here. Negative 1 is 0.368, so comes up a little bit from the previous point. 0, 1. Back down here in the table, 1 gets plotted with a 2.718, so that would probably be about right here. And then 2 in my table gets plotted with a little over 7, so it's going to go up higher. So this graph becomes more steep compared to the previous graph. Okay, it's getting higher more quickly, because this base of e is greater than a base of 2. Likewise, on the other side of the y-axis, notice how the graph hugs the negative x-axis more closely than the previous example here. So I'm going to try the best I can without touching, because I'll never touch the negative x-axis for this graph. I'm going to try and draw it without touching. Okay, we're not stopping here. We just plotted enough points to get the idea of the graph. Do we have any asymptotes? Yes. We have an asymptote of the x-axis, so we call that y equals 0. Okay, 2 more. This is the equation y equals 3 to the x. It must be something about the table that's making this stuff jump. Okay, so let me finish these two in this video, and then we'll look at the back in the next video. Okay, 3 raised to the negative x. So that's 1/9. And 1/9 is 0.1 repeating. So smaller than this value. 3 to the negative 1 is 1/3. We all know what that decimal is. 3 to the 0 is 1. That'll be an easy plot. Notice that all the graphs so far share the 0.01. 3 squared is 9. If I tried to use the same scaling along the y-axis, this graph's going to rise more quickly, and I'm going to try and do that. Alright, plotting these two y values at -2 and -1. Notice how they compare to the previous two y values. They're smaller, so this is going to be difficult to graph, but I'm almost on the negative x-axis. Likewise here. Oh, let me get my scaling over here. Going by ones. So I'm going to plot -2, 0.1, I did, -1, 0.3, and then 0, 1. And then when x is 1, I'm up at a height of 3, higher than the previous example, and 2 is going to be at 9. Well, that's going to be off my screen. Let me see if I can get this come back down. That's 5, 6, 7. It's going to be way up here. Notice how steep this graph gets. Let's connect the points. Let's not touch the negative x-axis over here. That serves as a horizontal asymptote. So what we should be seeing is that as the base gets larger, I went from 2 to 2.7 something to 3. As the base gets larger, well, then my y values get greater, so my graph should become high really quickly. And even look at this base now. This graph right here should even be more steep than the previous 3. Okay. Oh, let me come back here and record the asymptote as y equals 0. Probably wouldn't hurt to go ahead and record this asymptote as y equals 0 as well. Okay, so this function is 10 to the x. I don't know how I'm going to plot that. Even that one. And I certainly won't be able to plot 10 squared or 100 if I'm using the same scaling as the previous 3 examples. So when your base gets large like that, greater than 1 and larger, your graph is going to increase and be very steep. -2 and 1/100th. I'm not on the negative x-axis, but I'm just as close as I can be. -1 plotted with 0.1. Same thing. Let me create my tick marks. That's 4. That's 7. Okay, plotting 0, 1, 1, 10. Well, 1, 10 is way up here, and 2, 100 is going to be way off my screen. It just gives us the suggestion that the graph is very, very steep. So I'm increasing and getting very, well, it doesn't come backwards, obviously. Very steep. Okay, some observations that all 4 of these functions are increasing. They all 4 share the 0.01, and they all 4 have the same asymptote, y equals 0. Okay, they're all increasing because these bases are all values greater than 1. In the next video, we're going to look at exponential functions where these bases are less than 1 but still greater than 0. So we'll see that in a minute.